Shall we? Yeah, you can keep discussing later. Okay, so the second talk is going to be about modular construction of multi-threaded free extensions by Ohad Kammar.
Okay, is that okay now? Sorry about that. So thanks for letting me speak. This is a short paper. The paper has many more details, and I think I would want to spend the talk just giving intuitions and examples, maybe even interactively to some degree. And the previous presentation I gave on this topic, also in PEPM sometimes, were a bit more technical, and I'm coming in from a different angle today. So in fact, I want to spend a lot more time maybe on just introducing free extensions. And if you really care about the modular construction in the technical level, then we can talk later, or we can look at the short paper. Okay, so this is great. Okay, so oh, it's quite big, yeah. So frex, free extensions. That's just a comment here. The way I understand it now, it's a theory of data structures for intermediate representations. Okay, so that's kind of the connection to partial evaluation. And by intermediate representation, what I mean is open terms. So the terms have variables in them, which means we have to do the partial evaluation. We can't just do evaluation. But we want to take into account semantic equivalences. Okay, so the plan today, as I said, I'm going to start by trying to motivate the theory directly from first principle in partial evaluation. I think I've not done that before, and maybe that might be more intuitive to some people. And if there's time, I will go into the details, or some more details of modular construction of free extensions. Okay, but really the aim for the first bit is to be much more introductory and interactive and intuitive. Okay, great. Okay, so I wanted to take maybe a neutral example. Okay, so this is probably nothing that you have exactly interacted with, which I call an action box. But I'm sure that, especially if you're in university, you've interacted with something like this. And if you're in industry, you can make a lot of money by selling this to universities. Okay, so what's an action box? It has three things you can do with it. You can flick a switch. Okay, and then a light turns on. Okay, you can press a button and it increments the counter. Okay, increment. This is written in Idris, by the way, Idris 2. So this is a shout out to Edwin, who's the co-chair. Okay, and then you have a little knob on the end that you can turn, and you can turn it by some degrees, say 30. Okay, and then it increments the counter, but it keeps track of how much you've turned it. Okay, so the pressing the button doesn't change the dial, but turning the dial does. Okay, so that's just an action box. It's completely useless, okay, but hopefully we've all coded things that look like this, but it's not useless, hopefully. Okay, and what I would try to do is to show that even this, if we think about this in the context of partial evaluation, has nice algebra in it, okay, and the algebra just comes out naturally from it. Okay, there's a little bit numbers in there already, but the numbers are not essential to get the algebra out. Okay, any questions so far? Do you want me to run something on the action box, something specific? Any requests? No? Okay. So again? You mean this? Okay, great. Okay, fantastic. Okay, so yeah, so what's happening inside the box, right? There's a really we can represent it. This is how I represented it. Right? There's a boolean telling me if the light is on or off. There's an integer for the counter. There's an integer for the dial. Okay. Oh, I should use the mouse because people are at home. Sorry. Okay. Okay, and then I can apply these commands to the state, and the state changes. What I flick the light, I add to the counter, and then I can add whatever I added to the dial, but in both components. Okay, and just to make my life easier, these actions I can do them in any order. You have to think about it a little bit because it's not so immediate, but it is quite immediate. And that makes my life easier, but it's not essential. Right? So if what you're doing doesn't happen in all orders. Come, there's lots of room at the front. You can come in. Okay. So of course, we're all lazy. You know, we're flicking the button is annoying. So we want to write some script to automate this. Okay. So we write a script. So what's a script? It's just a list of commands, and we can execute a script on a state, and we get another state out. Okay, and I'm using functional programming because it's a with, so I'm using a fold. You can use a while loop. That's not essential here. Okay, so here's an example. I can flick the switch, ink, 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 flick, and if I apply to the initial state, which was 0, 0 everywhere, what shall we get? Anyone knows? From the audience? 3 in the middle, exactly, and 0 elsewhere. Yeah. Fantastic. So the box shows 3, but the dial is at 0, and the light is off. Okay, great. Okay, so now let's think about partial evaluation of the script. Oops, sorry. Partially evaluating the script. Okay, so what happens here? I don't know the state, okay, but I know the script. So I shouldn't really just keep a list, okay? I should be able to evaluate it, even though I don't know what the state is. Okay, and what pops out is algebra. I mean, I think this is really the point of algebra. But when you learn it as an undergrad, it's kind of given you the other way around. But really, this is where it's coming from. Okay, so I have my list of commands, but I'm going to represent them. This commands type, okay, is much more compact than a list of commands. It's taking it into account the equivalence that I know hold when I interact with the state. Okay, so specifically what I'm going to represent it as a 0, 1, so an integer modulo 2, okay, which is either how many times I flipped the switch, okay, because this is the effect that the script is going to have on the state. And that is how many times I press the ink button, and the integer here is the total sum of me turning the handle around. Okay, and a single command embeds into this just by putting the right numbers on the diagonal. Actually, there's a typo here. No, actually, that's correct. Ignore me. This is fine. This is not a typo. Of course, it's not a typo because this is the code that runs, that makes everything work. So, yes, one of the fun things of using a new language is that you have to write the code listing generator for it, so you can write the papers about it. So you get to inject your workflow into it. Okay, so I can interpret all the basic actions, but also I can look at the empty script, okay, which is just does 0 everywhere, and I can sequence two scripts together. Okay, and this is the operations that I get, and now I can do partial evaluation on this script, and I get 0, 3, 0. Okay, this is the action I'm going to do in the state. Okay, once I run it on the first state, it's going to add 3. Okay, this is not the state. This is the action I'm going to apply to the state once you give me a state. It's a partially evaluated script without having the state for the box at hand. Okay, and you see the algebra just popped out. This is a monoid action. Okay, so the action, the commands from a monoid given by sequencing. Okay, and I'm acting on the state. Okay, we're really doing algebra. Okay, usually when you learn about algebraic structures in undergrad, it's the other way around. Someone came up with a monoid, and you later on, if you get to algebra 2, if you're doing some math and computer science, you learn about monoid actions and group actions and so on. But really, it's the other way around. You have some sets of states, and something acts on it, and it might be just associative on it because you're just applying actions, or it might have some symmetries, so it's a group. Okay, but really, it comes from partially evaluating the things you're doing to that state. Okay, that's really where it's coming from. That's like, Kylie's theorem is really about that, right? You represent a concrete collection of actions using an abstract group or monoid. Any questions about this, actually? The room is nodding, which is a breakthrough for me. because usually I start talking about algebra and people just immediately glaze over and not listening. And some people say, yeah, algebra, partial evaluation is algebra. That's a breakthrough for me. So maybe some... Say again? Oh, the box, yeah. This is the box. Okay. Say again? Okay, yeah. What do you want me to do? Yeah, well, yeah. Any requests? I'm riffing on the box. Ink, yes, ink. Turn minus 10, fantastic. Oh, it's got negative, great. Yeah, anyone else? Anyone particularly nasty? Minus 700. Let's see what happens. 700. Oh no, there's an error. right? But it's only an error on the display, right? Because if I turn it 150, oh no, that's not enough, right? 800, oh, it's back, okay? Oh, another 800. Oh, there's an error the other way, but, oh, okay. So Idris implement begint, okay? So you know, it might run out of memory, the computer would run out of memory before the action box will break, okay? Okay, so far so good. Okay. I'm quite surprised that this is what, but you see, I mean, you can see that the action box is very useful. You can relate to it in your daily life. Yeah, this is. Or maybe I should put the code out there. Okay. Okay. So far, so good. So the commands, the partially varied commands form a monoid, and the monoid acts on states. Okay, and that's what we have here. So really, kind of the key idea, and I say partial evaluation, but I really mean just one part of partial evaluation because I'm not an expert in, you know, the previous talk. I'm completely humbled by what's happening there, right? And Adam's talk in the morning. But specifically, the part of looking at a piece of code with some open term in it, right? This is really, you replace partial evaluation by evaluation in an abstract domain. Okay, we verify the actions into their own monoid, and now we're evaluating the scripts inside that monoid. Okay, we turn our state to be abstract. But now let's add also the actions, the commands, to be abstract as well. Okay, so let's look at open scripts. Okay, so what's an open script? It's a list, okay, that either has a command or a variable that stands for a chunk of script that I don't know. It will be dynamically determined in the future. Okay, so for example, fleck, and then do x, 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 whatever x is, whatever the action is. Okay, I need someone to give it to me. The binding analysis means later. Okay. So you can think of it as an unknown, you can think of it as dynamic, and the variables for those things are taken from this set A. Okay, see Andy Pitts in the audience, I have to have the support explicit, so maybe also that will make up for the apology I owe him, so sorry, Andy. Okay, so now we want to look for an abstract domain for open scripts, and if you do partial evaluation for a long while, you're going to be laughing at me because you'll be saying that I'm playing with like Lego bricks, basically. I mean, you've been doing this for years. Okay, so I'm going to show you something that you've been doing for years, but it's more of a rational reconstruction of what you've been doing for years. Okay, so what's happening here? Well, we have two domains here. We have commands and states, okay, and they both can have variables in them. Okay, so I'm going to define abstract domains for commands, which I call O, because it's a monoid, and states, okay? And this is how I'm going to define them. So give me some variables, command variables, and some state variables. The abstract domain for the monoids is going to be a command, okay? So one of those compressed commands, together with a bag, so a dictionary, a multiset, right, of the command variables that appear in the script. And that's because I'm taking advantage of the fact that that my actions, my monoid is commutative, so I can move things around and push one thing to one side and everything else to the other side. Okay, and you know this because it's been done in, you know, given a name in 88, which means it's been done since the 30s. Partially static data structures by Morgenstern, and we all have done this kind of technique. And for states, it's a little bit more complicated because the variables, the kind of the open terms I can get inside states, they can come from the state variables, but can also come indirectly from the action variables, from the command variables, right? Because the command variable can act on a state, and suddenly they both live there. So there's two options, really. Oh yeah. So the command bit is the dynamic, is a statically known command, all commands grouped together, and the bag is all the dynamic variables grouped together. On the other side, it's a bit more complex. So there's two cases, and it's really depending on whether the state, right, is dynamic or statically known. Okay. So if the state is statically known, okay, then all the concrete commands that I have, I can just apply them to the state. So all I need to keep track of is the command variables that I have that I've applied to that state. Okay, everything else gets bagged together with the state that is concrete. But if the state is abstract, okay, then I have to keep track of everything. So I'm going back to the partially static representation of the commands. Okay. Yes, Cody? You're shaking your head. Please verbalize.
This isn't commutative, right? I feel like you have commands, and then
Yes, but the effect on the state is cumulative because I designed it to be that way. It doesn't have to be, and then you will get something more complex. And actually, we do that in the paper. You can go and look at the representation you get for the non-commutative case. It's just a bit more hairy, but I think this has enough meat to seem.
Yes,
yeah.
I agree.
Correct. And I mean, that's because the operation on the monoid is commutative. Yeah. Okay, any questions so far on this? Maybe hands up if someone has done something like this before. I don't know, in a partial evaluator. Implemented a partially static. Yeah, Jacques did, yes, and Ruth did. Anyone else? Okay. I'm sure you all did, but you might be shy. Yes, Neil did. Okay. Oh, was that a question? No. Okay, you did too. Okay, okay. And then you can now, it's like any good data structure. Once you fix the data structure, then the operations write themselves. Okay, so I have a, if I look at, yes? No, a script. It could be a whole script, yeah. Mm-hmm. Yep, that's correct. You're following great. Very good. I'm loving this. Okay. So now the interface to the data structure, the operations we can do on the data structure, write themselves. So what do we need? So let's look at commands. It's a little bit easier. I have a static. I think if you look at if you look at the literature, this is sometimes written with an underline, right, where you kind of promote the constant into the partially static representation. So you're kind of lifting, or we call it static because Idris doesn't really have a fancy notation. You have Unicode, but it's not as good as ASCII, apparently. You can promote one of those kind of partially varied commands into an open script. Okay, and it's kind of straightforward to do it because I just stick it on the left component and put the empty back. There's no variables in that representation. Okay, and dynamic, it's the opposite, right? I put the skip, the empty script on the left, and just stick in the single variable that I embed. So, and because now I can put single variables and whole scripts, everything else just kind of, again, writes itself. I take the union of the multisets and compose the scripts together to get the composition in the partially static data structure. And something very similar is happening on the right. It's a little bit more involved, but I will not go through it in detail unless someone has a very strong urge to go through that. No. Okay, but it's the same thing. Okay, and now you can write a partial evaluator. Okay, so how do we partially evaluate a command? Okay, I have some script and it has some variables. Well, I just fold over it. But then if I have a concrete command, I just embed it and then start it, lift it. Okay, and if it's dynamic, I just dynamically embed it. And on the state, it's the same thing. It's so much the same structure. It's just a fold that applies the star and the dyne, so that it's almost generic. And not too long ago, David Calope Meshiniak, who's I think still a student in Cambridge, and Jeremy Yallop, right, kind of pitched the fact that you should be doing this generically, partially static data structures, and also made the entry point into this work. Okay, so I implemented these two functions, and now we can evaluate this script on the initial state, and what we get at the end, right, is it's the same initial state, but say you need to, but you also apply to it the abstract fraction x 3 times. Okay, but the flick disappeared. That's the point, right? I have flick in my script, but in the residual program, there's no flick. I optimize it away. Maybe I've jumped a little bit, leaped a little bit here.
This is the dynamic partial evaluation, right?
This is dynamic partial.
In the sense that you're given the value and then you partially evaluate, or you're only given the information that...
No, you see, I don't have the value. So here I chose to insert the initial state. I could also have taken the right y there, and it would still evaluate. I don't have to stick in a value for y. Yeah, so it's static. sorry for not necessarily using the right terminology. So one of the reasons of coming here is to pick it up by osmosis. Okay, great. Okay, so let's now, so this is kind of all standard. Some people have literally written this code. Other people, I'm sure, have written this, but it might be broken slightly differently in your various modules inside your partial evaluators, because what else would you do, right? I mean, really. Yes?
So if there were concrete actions in your script
like
which
this one?
didn't cancel out,
Yep,
they would then affect the initial state and it would no longer be the initial state.
that's correct.
Thank you.
Okay, because the initial state is concrete, okay, is static. If it was abstract, then I wouldn't be able to just apply them. They would get all shoved to the partially static representation of the script, okay, of the commands. Great, I'm loving this. Okay, but let's zoom out. Kind of, this is where the algebra again pops out. Okay, so I've not. This is the code that you will write. It may be broken slightly differently, but this is it. And I'm just going to rearrange it in an algebraic way so you can see a completely uniform picture for partially static data. Yes, Cody?
I'm sorry.
Yep.
If you wrote write y and then write x and whatever.
Here.
Yeah.
Mhm.
Here, instead of the write x,
It would be
X.
write something. It would be something very different. Yes.
Yeah, it'd be a y and then an x.
It's going to be a y, and then it's going to be a 0 and an x, and a bag with 3 x's.
Yeah. Okay.
Okay?
But if you did it in the other order, it would be.
The order doesn't matter.
Oh yeah, because it's a bag. I see.
I mean, on this side it doesn't matter, and also on the script side it won't matter.
Yeah. Okay. Thanks.
Okay. Great. More questions? Okay, so let's just put these things together. We have the original concrete command states and an action. Okay, and then in the abstract domain, we have the same pattern, right? We have a command state and an action. Okay, and we have this lifting, this static operation that moves us from the concrete domain to the abstract domain. Okay, and that's you need to check, but that operation preserves all the monoid operations and the action operator, the monoid action as well. So it's a homomorphism. Okay, and on this side you have a function that lets you embed the variables into this, and you use them. You use them when you write the evaluator. Okay, it might be in your code. It's slightly more inline in a slightly different way, but it's there. Okay, but this picture, which I'm going to zoom on, it has a name. It's called an extension of A by X and Y. Okay, and theorem, this is a fact. Okay, that the representation I gave you before, if you call it up in math, okay, and in Idris it's a bit easier to think about it in maths because it's dependent type, so you can kind of interpret it really as mathematics. I didn't use any partiality for this code. Theorem that the data structure I use with this star and this line is the free extension. Okay, it's somehow the initial one, the one that only involves these operations and nothing else. Okay, so somehow I have a spec. Let's kind of ponder this. We have a spec for this data structure. We still have to implement it. If you know a bit about free structures, then not automatically. You have to kind of be a bit creative in pinning them. You have some abstract constructions for them, but if you need to implement a data structure, they're useless, nearly useless. Okay, but you still need to design something. But when you design it, you can then check, prove, is this the correct one? Okay, so it kind of turns this kind of craft of building partially static data structures into a bit like an engineering. Did I solve the problem or not? Okay. Yes, Ben. The previous slide? Okay.
So can you think of this as free extension as just terms of
Yep. Yeah, modulo the equations. That's exactly how you can construct it. But like any quotient, it's not really helping you if you're trying to simplify the code, because you take the term and you move to the quotient and it's the same. And what you want is a simpler term or a better representative. Okay, so you can go into the quotient, but then you somehow need some simplification, some effective procedure that moves you into the values that you need in order to partially evaluate.
Isn't that exactly what we were doing in the previous slides with your commands? Wasn't that?
Yeah, that's exactly where it came from. Okay, so and I'm going to flip this now. Okay, I now identified partially static data with free extension, and now when I come to a new situation, I start by trying to find out what are the operations, what are the equations, what is the free extension, and then I calculate the data structure. Okay, then I know it's sound incomplete for what I've chosen to include. Okay? And it's this kind of the first steps of a theory of partially static representations. Okay? People are nodding. That's really impressive. Really, I mean, usually it's completely an uphill battle, and I kind of get kicked out of the room at the end. Anyone? Challenge? Yeah? I mentioned monoid. That's already 3 equations. Like any free construction, there's creative. I mean, you could do what Adam did, right? And you say throw in the equations in. I was a bit of a maybe nice audience member, and I didn't challenge him. Does he know really how much he solves that theory? Because you know, he gets a sound proof, but I don't know. I mean, I was going to ask him later. Is it complete? Okay, and here, if you have constructed the free extension, it is complete. Okay, it's guaranteed. You have used all the equations. You've not missed out anything. And in fact, it's the opposite. I mean, you have a conjecture. This is the free extension. You try to prove it, and then you realize, oh, it's not. I'm missing some equations. I can quotient my representation even more from experience. But maybe it's because I'm a bear of little brain. Any more questions? Maybe online? I don't know. Okay. Modularity. Okay, I'm going to talk about modularity high level. I don't think we're going to have time to really go into the deep details, but you can talk to me later, and there is an abstract. Okay, so what are we doing here? What do I mean by modularity? Okay, step 1. And this is not today's work. This is things we've already done. Okay, take a partial evaluator. It's a complex mix. I mean, we've seen in the last talk and many talks before. It's quite complicated, lots of moving parts, and I'm really focusing on one part of it. I mean, I'm not saying this is a theory of all of partial evaluation, just of partially static data structures. Inside it, there's a cogwheel that's partially static data. And what we're doing is we're refactoring out into a separate component. Okay, using the concept of a free extension, and you have this interface: static, dynamic, operations, equations you agree on that are invariants. Okay, that's step 1. Refactor it so that the frex is now separate. The partially static data representation is separate from your partial evaluator. Okay, great. Step 2: do multiple of them. Okay, do it for monoids, do it for commutative monoids, do it for rings, do it for semi-rings, do it for lattices. Okay, that's what we've done. Okay, but the partial evaluator stays fixed. You can write a generic partial evaluator, okay, that you just plug in your partial static representation, and it works. It knows about terms, it knows about equations, it knows about staging. It almost looks magical. Okay, that's in this paper with Kammar von Glen, who's now in, I think, Google Brain or DeepMind. I don't remember. I have to. Sorry, and Jeremy Yallop. Okay, from 2018. That's step 2. We've done that already. Okay, this is not the modularity I'm going to talk to you about today. Step 3. Okay, do more than just one partial evaluator. Okay, so we did one for staging. We did another one for extracting equational proofs. Okay, proof synthesis. Yeah, go on. If you view it as Knuth-Bendix completion, that's kind of like what it's doing, right? I know. I'm not. Fantastic. I'm loving this because my punchline when I get to what I am going to talk about, well, I'm not going to talk about it, but what is in the abstract, is that modularity is not at all trivial, not at all obvious, not at all to be expected. It needs to be celebrated. Okay? When you find it, it's a cause for celebration. Okay? Great. This is fantastic. Okay, so, and we also are currently working on normalization by evaluation algorithms. Again, you kind of write a generic normalization by evaluation algorithm, and you plug in the frex. And Adam also touched on it. It's kind of, you kind of corner him or something and have another go. Okay. What I am going to not talk about today is modularity in this sense. Okay, I'm sticking another component in the middle between my frexlet module, and the partial evaluator, and it turns one frexlet, one free extension module, into another. Okay, it's almost like a little adapter. Okay, and you need to celebrate this because it's not obvious that you can do this. And we have 2, and we're working on another one. So one is for involutive algebras, one for homomorphism graphs. I'm not going to tell you what they are, but that's in the abstract. And one for ring solvers. Okay, and that's by far like so much more complex, but I think is like so much more satisfying if we get there. Okay, and it involves operads and multi-categories and United structures. I'm having lots of fun with it. But really come and talk to me afterwards. So I'm going to skip the actual details, sorry, and go to the conclusions. Okay, so I'm surprised that I did manage to at least not get objection that partial evaluation leads to algebra. Usually it's I kind of go it the other way, and I suffer. But that seems to have gone down well, so I'm counting it as a success, at least for the room. I've shown you how to view partially static data, okay, as free extensions or representations of open expressions, modular semantics, and then I just highlighted the fact that you can do some things modularly, which is to be celebrated. And I'll take more questions now.
Thank you for a great talk, but I have a question about, so the only commutative actions are considered as partially static data, or is there another theory that describes action for non-commutative settings?
You can have so is the question, you did it for commutative, for actions of commutative monoids. Can you do it for actions of non-commutative monoids? Is that the question?
Yes.
Yes. It's a bit more, so, okay, this is a bit unfair. It's a little bit more involved. What happens is you kind of, you have alternating lists, okay, between bags between non-empty bags of variables and concrete elements of your monoids. Okay, so as a representation, you need to be able to decide whether you're in the unit of the monoid or not. Okay, but sorry, not bags. Yes, of course, lists. Thanks. Yeah, non-empty lists of variables. Thanks. Okay, and we have one concrete construction in the abstract, and we have two other concrete constructions. One in the unpublished paper on proof synthesis, another one in the one about staging. You know, I vary the representation every time because it keeps it more interesting for me. Yep. Mm-hmm.
So, what is the takeaway here? Is the takeaway that that partial evaluation induces some kind of algebra? You also have some tool in Idris and Haskell. What are we supposed to take away from this? The ideas and to apply them elsewhere, or are you saying that you have some partial evaluator that we should just use?
Yes.
Yeah. Okay. Thank you.
So yeah, I mean, fantastic. The message has gone through. Thanks.
So the green boxes are the different frexlets that you mentioned. Those are different kinds of partially static data structures that one might want to work with. Mm-hmm. And the blue ones are different partial evaluator strategies.
What you would do with the partial evaluation, because you can do partial evaluation for so many things. You can even do it for type checking, like that. I mean, I knew you can do it for type checking because of conversion checking, independent types, but I didn't think about it like this, so that's quite nifty. So I've not done it for inference, right, for type inference, but we've done it for equational proof synthesis, which is then used in type checking, or at least in discharging propositional equalities in dependent types. And we're doing it for normalization evaluation, which is kind of a generic normalization procedure for higher order programs.
Okay, so the blue is different applications of partial evaluation.
Yeah, exactly. Yeah, different applications of partial evaluation.
And so could you spell out a little bit in more detail the motivation for the orange? Like, why don't they currently fit together, and what is the need for the adapters?
So what happens as your theories get more complicated, the structure of the free extension gets more complicated, and so it's very easy to cut corners. Right. And what you implement is actually not complete, and you're missing out on opportunities to shrink things. Whereas if you can construct it modularly, you can have a very small one, you're very careful about how to do the alternating list with monoids, suddenly, bang, you get your semi-ring solver, all fine. Okay, you add involution, it's all fine. It's guaranteed to be complete. You kind of maximally compact. This is not about optimization. It's about bringing different things together so that then you can then traverse it and generate the efficient code, maybe with maximal sharing and so on. Okay? It's really about finding that representative for the equivalence class of open terms.